Good morning. Today I will talk about the new standards, new rules that we can apply in the current application scenarios for pipelines, for metal pipelines. When more than 20 years ago I started working in the field of measure instrument for catalytic protection, there was the idea that catalytic protection was for catalytic protection experts, and that we had to focus only on electronics, on metrology, and in the following years on telecommunication systems. And so my first reaction in front of those data was scratching my head. Something has changed during these 20 years, and I think that one of the main reasons is the introduction of massive system of remote monitoring for cathodic protection. Mainly this started with the introduction of specific national rules in Italy. I will start by explaining why we make cathodic protection, then I will talk about the standards that we are used to use today. Then I will explain some new standards that we have developed during the last year and that we are developing, and I explain why we are developing new standards. So, why we make cathodic protection? Usually the explanation is that the metals we use in pipelines aren't pure at their natural state. They are present as oxides. We purify them, giving energy to them, and nature try to return them to their original state of oxides. But there is another important reason, perhaps more important reason. The fact that there is corrosion costs 6 to 7% of GDP. If we try to give it more factual explanation, in Italy we could say that the majority of employees receive 12 salaries per year, a 13-1 and a 14-1. So 14, each of these 14 salaries is around 7% of what they obtain for their work during a year. So it's like every one of us, it's working 1 month per year only to pay for prevention, maintenance, repair of corrosion. This is something that comes from a lot of different researches, and it's the same for countries with different characteristics as US or India. But what's interesting is that the first studies made on this phenomenon were pointing out that the main field of costs of corrosion was automotive. Today, with the change in materials and technologies, these costs have disappeared, and the main sector is its utilities, its pipelines. And the good news is that 25% of this cost can be avoided if we use current technologies. The standards we are used to use mainly come from the observation of Daly long ago, more than 1 century ago, and from the discovery that if we decrease the potential of the metal of the pipe with respect to the soil, represented by a copper sulfate electrode, by 100 millivolts, we have a reduction of 10 times in the corrosion rate. So if we are in mildly aggressive soil at minus 650 millivolts with respect to SE, decreasing it at minus 850, we will decrease 100 times its corrosion rate, so 90%, while 99%, while if we are in a more aggressive soil at minus 450 millivolts and we decrease it at minus 850, we will have a reduction of 10,000 times of the corrosion rate, so 99.99%. From this observation, empirical observation, we started producing standards, and also the academic research demonstrated that there are electrochemical phenomena that can explain these values. The first main rule in Europe is EN 12954 on general principles, and it's accompanied by 13509 on measurement techniques. They are based on this principia. They tell us how frequently we have to monitor the effectiveness of the cathodic protection, and how we can measure the potential to evaluate the effectiveness of cathodic protection. Then there are situations that were less common, so we developed the 5162 on stray currents, DC stray currents mainly produced by transit systems. We developed, because we had so many standards to know, we developed also a European standard 15257 on certification of cathodic protection personnel. And then we started looking at AC interference. So we developed the 50443 on AC interference, and mainly it gives us the criterion for safety, how much we have to reduce the induced voltage to be safe for human contact. But there is also the risk of corrosion due to AC interference. We developed recently the EN 15280 to assess the risk of corrosion by AC interference. And here there is an interesting fact. All the other standards were standards based on potential measurement, but for when we are in presence of AC interference, the criteria totally change. We have to use criteria based on current density, and this is a problem because it is not an intensity, a current intensity, but a current density. So the intensity on a surface, an area, the area of defect, the surface, the total surface of defect. So because we don't know the total surface of defect, we had to invent something to take this kind of measure. And the idea was that of using small pieces of metal of known size connected to the pipelines by a cable, and so we can measure the current intensity flowing through this cable, and knowing the area of the size of the coupon, we can obtain the current density, both the protective current density in DC and the induced current density in AC, because we have three criteria: one on DC current density, one on AC current density, and one on their ratio. And the interesting fact is that the use of coupons and of probes, coupons integrated with reference selector, gives us the possibility of reducing the error that we introduce when we measure with a reference selector with respect to the metal of the pipe, because we measure, yes, the potential of the pipe with respect to the soil, but we also add to it the ohmic drop inside the soil. The ohmic drop is due to the resistivity of the soil that produces a resistance between the 2 points, and by the currents that flow between the 2 measure points, mainly the protection current. So using coupons, we can put our metal nearer to the electrode, so reducing the resistance. And we could also use electronic switches inside our measure instruments to cut the connection between coupon and pipe, and so remove the protection current from the ohmic drop. In Italy, we introduced 2 other national standards. They start from the table in EN 12954 that gives us the periodicity, the frequency of monitor or control on each test point. And this table in a note says that if we have a continuous measuring system, we are no more obliged to take all this manual control with this frequency. In Italy, we developed 2 national standards to better define what is a continuous monitoring system and what kind of verification we have to do when we have a remote monitoring system. As I said before, during the last years, there has been an evolution in standards, because what was an exception in the previous context, now it's almost usual. As an example, the previous standards were developed in a period where the majority of coatings were bituminous coatings, so porous coating, while nowadays we tend to use almost perfect coatings as polyethylene. But also because in the past there were less sources of interference, while nowadays we have a lot of interference between different systems, both in DC and AC. So we started revising all the standards. The first standard we revised, the more important standard we revised was that on general principle we passed from a European standard to a ISO standard 15589-1 for onshore pipelines and -2 for offshore pipelines, and it gives us general principia and measurement technique for pipelines. The problem is that it's only devoted to pipelines, so we are revising the European standard to cope with all other structures. Also, there is an ongoing process for changing the 5162. It will be a IEC standard, perhaps, and only dedicated to railways. So we are developing another ISO standard on stray currents, the 21859, that it's dedicated to all kind of DC stray current sources from transit system to aeolic fields, to tidal waves, to geomagnetical currents, and so on. Also, we pass from a European to an international ISO standard for certification of personnel. We pass from the 3 levels of the European standard to 5 levels, and now we are in the 2 years period where we need to pass from the old certification to the new certification schema. And also the EN 15280 had a short life because has been replaced by an ISO standard 18086 on AC corrosion risk. We are also revising the Italian standards, and we are going toward a unique standard that it's focused on gas pipelines, but all its principia are applicable also to water pipelines and hydrocarbon pipelines and so on. And why? There is also a growing interest on the use of coupons and probes, as I explained before. So we are working also on an ISO standard on measurement techniques on coupon and probes. Why we had all these changes to the standards? There are 3 main reasons. The first reason is the need to have an harmonization of standard due to globalization. A lot of companies nowadays work worldwide, and they cannot cope with the need of coping with different standards, different certification schema, and so on. The second reason is that, as I said, we need to cope with the new application scenarios because of the growing presence of interferences and the growing presence of defect-free, almost defect-free coatings. And the idea of the old standards was that we had to make a very thorough control, a reference state control every few years, and then only verify that we weren't so far from this reference state. While nowadays we are sometimes in a situation where we cannot have a reference state because the environment is too dynamic to find a reference state. The third reason is a legal reason. There were incoherent and not so clear standards in the past, so some operators have been condemned for where there were accidents with casualties. So we want to have standards that are more coherent and more clear to understand.